So we're still within ionic compound naming. We're close to being done with it, but there are a couple other situations we need to discuss. And the first is ionic compounds that contain polyatomic ions, right? Polyatomic ions are these interesting things. They are covalent compounds that have an overall charge. So they themselves are covalent compounds, but because they have an overall charge, they kind of act as big negatives and big positives just by themselves. Okay? So if they have big negatives and big positives, they have an overall charge, what kind of compounds are they going to be involved in? Ionic compounds. So to make these ions, they're sharing of electrons, but the overall structure is thought of as just one big charge, one big sphere, right? And so it wants to attach to a sphere of opposite charge, it's going to be involved in ionic compounds, right? We change up our rules yet again. We're not going to do root plus IDE with these guys, but what that means is that you have to memorize some things. So essentially on slide 22 of chapter 2 slideshow, all right, what you'll see is a list of polyatomic ions, okay? You should memorize these, all right? And then in our naming rules, because we're not using root plus IDE, the reason we memorize these names is because you just use these names without modification, all right? Essentially, kind of in a way, the root plus IDE is already done. There's a lot of other things that are happening in the background with how you come up with these names. But again, the take home point is you need to really memorize these, be able to identify them, be able to know their name and their charge. When you memorize these guys, memorize their name and their charge, because that's really what you need to sort of come up with formulas in ionic compound nomenclature type problems. So let's do some examples. It's one of the situations in this class where I do recommend you kind of make note cards. And on one side, you have a name of the ion. And on the other side, right, you have the actual structure of the ion. And you go back and forth deciding between, okay, am I going to do structure to name or name to structure? And you really quiz yourself until it's all stuck in your head. All right, quick little example. All right, NH4Cl. Okay. So this is a very important compound because we would normally look at it and say, do we see a metal? And the answer right off the bat is no. But do we see something that acts like a metal? And NH4 is on your list of polyatomic ions. It's on that slide that you have to memorize, right? And NH4, right, is ammonium, all right? And this is NH4 plus. All right, it has a positive charge, so we say it acts like a metal, okay? So even though there's no metal present, there is something that acts like a metal because there is a cation present. Now, chlorine we know is always -1, okay? So what we have here is a situation where we have NH4 plus, which is itself a big charge, and then we have Cl minus stuck to it, right? So it's definitely an ionic compound because NH4 acts like a metal. So what we do here is we name it like we always do, but then we just use the polyatomic ion name. So it's going to be ammonium chloride. All right, ammonium chloride. Okay. Let's look at something like K3PO4. And then after that, let's do FeSO3. Okay? So I look at these compounds and I go through my normal sort of naming identification steps, and I see metals present. So definitely ionic compounds. Okay? Let's focus here. This is metals attached to, all right, a polyatomic ion we have to memorize. This is one big chunk of charge, right? And the name of this is phosphate. So what I'm going to do is I'm going to name this like I normally would, potassium. I'm not going to name this phosphide. I'm not going to do root plus IDE. PO4 minus 3 is something you'll have memorized as phosphate. So if I know that that's phosphate, literally all I do then, just like ammonium, is you just throw the name in there. This is potassium phosphate. Now to go in the other direction, we need to know that phosphate is -3, which is why you memorize phosphate not as PO4, but you memorize phosphate as PO4 minus 3. Memorizing that charge along with the name is really important, right? What about this, right? We see that we have iron here. Oh, we do that extra check. Iron is what type of metal? It is a transition metal. It's in that B block. So I have to know something about SO3. And actually, SO3 is on our list, and you're going to be a good student and memorize that SO3 has a charge of -2, and its name is sulfite. So if SO3 is -2, that means that this Fe must be +2. So this is going to be iron 2 sulfite. All right, iron 2 sulfite. So again, there are good things and bad things about polyatomic ions. As soon as you know the name, then you just use that name directly in your name of your compound. You know what I mean? There's no monkeying around with root plus IDE or anything like that. You literally just use the name of the polyatomic ion in your compound name, all right? But the bad thing is that you do have to memorize them, and there's really no way around those memorization steps, okay? So try to just, digest that slide 22 as quickly as you can, get those bits of information in your head. Let's do one other example. Let's go in the opposite direction. Let's do, let's do chromium 3 hydroxide. All right, chromium 3 hydroxide. So chromium 3, that must be a transition metal because I'm giving the charge in the name. So I'm going to write this as Cr plus 3. Hydroxide is something we'll memorize as OH minus, right? Now, OH minus, how many of these do I need to balance out the charge there? Well, this is plus 3, this is -1, so I need 3 of these. So I'm going to make a mistake in how I write this, CrOH3. Now, why this is a mistake is you kind of are losing information here. Is it OH3, right? Well, no, we really want 3 of these OH minuses to balance out this plus 3. So in our formula, what we do is we use parentheses. Remember, we view these polyatomic ions as big chunks of charge, right? Cr is going to be attached to 3 OHs. Now, to make that abundantly clear, I encapsulate the polyatomic ion with parentheses in my formula, Cr parentheses OH3, and now there's no ambiguity about what that 3 indicates, okay? It indicates that for sure what we have are 3 different polyatomic ions, all right, stuck to this Cr, okay? The same thing happens with ammonium, so let's look at ammonium nitride. Okay, we're good students. We've memorized that whenever we see that word ammonium, that's one of our polyatomic ions. It acts like a metal because it's positive. It's NH4 plus. Nitride. Oh, it does end in IDE, so it's going to be just an N from the periodic table. All right. So N from the periodic table is in group 5, so it has a -3. Okay. So how many of these pluses do I need? Oh, I need 3 again. So what are we going to do? We're going to use parentheses. We need 3 whole big chunks of NH4 plus, right? We need 3 of these to balance out the -3 of the nitride. So we have NH4 in parentheses 3N, okay? So polyatomic ions, again, something to get used to. Memorization that we can't really avoid, okay? The last little bit of ionic compound nomenclature I want to talk about are hydrates. All right, hydrates. And hydrates are interesting ionic compounds, so we're still underneath our ionic compounds. And they're ionic compounds with water associated with their structure. So they're ionic compounds for sure. But somehow, when the ionic compounds form their structure, waters get stuck inside, all right? And now that's really just kind of like a simple way of viewing what happens with hydrates And actually, the beginning of next semester, you get into more of the chemistry of hydrate formation, etc. But for now, that's all you really need to know is somehow when the pluses and minuses are coming together, water is stuck, all right, between the pluses and minuses. You'll know a hydrate in terms of formula because what you'll see after it is a dot and then a number of waters. So then this is how we're going to name hydrates, okay? This dot and the number of waters tells us how many waters are stuck inside, all right, that structure as it forms. So you see that we have this part over here that we would name normally, and that's what you do. You kind of name the ionic compound part completely normally. Over here, though, we're going to add information. What we're going to use is a prefix here that tells us the number of waters, right? And then we always end in the word hydrate. So we name this normally, we do a normal name, and then we're going to use a prefix and hydrate to indicate that actually waters are stuck in this structure. So what do I mean by prefix here? We're going to use Greek prefixes, and you'll find them in slide 26 of PowerPoint 2, slide 26. And so 1 is mono, 2 is di, 3 is tri, etc. Things you might know already, but again, I included a slide in case you don't or in case you need those memorization steps just to kind of get those back into your head. All right, so then let's name this hydrate. And let's go through the whole entire thought process. Do I see a metal? Yes. Is it a transition metal? Yes. All right, so then that means that I'm going to name this with a charge included in the name. What is that metal attached to? It's attached to an SO4. I've memorized that SO4 has a -2 charge, and it's sulfate. So let's do this naming then. With all that in mind, I'm going to name this copper. What's the charge of the copper to balance out this -2? Oh, there's only one copper, so this must be copper 2 sulfate, right? Because the anion is just the name here. You just use the name. If there were no waters attached, we would stop. But now there's 6 waters. So what we do is we continue our name. Hexahydrate. How do I know to use this word hexa? I go and I look at that Greek prefix chart, right? And whatever this number is, I turn it into a prefix. So the whole entire name for this hydrate is copper 2 sulfate hexahydrate, right? Copper 2 sulfate hexahydrate. All right. Let's do one other example. Hydrates often form with transition metals, just to kind of be aware of that. Ooh, let's do AgNO3.2H2O, right? Look here, again, metal. Is it a transition metal? Yep, it's a transition metal. NO3 is the anion. It's a polyatomic ion. We'll eventually memorize this as nitrate. And as we memorize nitrate, NO3 actually just has a minus charge. So what does that mean about the silver? That means that the silver has a +1 charge. So we would name this silver 1 nitrate. If there were no waters there, we would stop. But we see there's actually 2 waters there. So this is silver 1 nitrate dihydrate. So it's just extra bits of information that we put onto words when these waters are associated with the ionic structure, all right? And so that's really it with ionic compound naming, all right? We have 2 more naming classes to kind of talk about, but there's a lot of memorization to do here and it takes practice. So I'll stress, just like I always do, make sure you're practicing homework, book problems, Chem 101. The more and more you practice these, the easier that they'll be for you.